Hi, I'm Cooper Caps,
And I am Jonah Grote.
I am Shiv Patel.
And I'm Ridwan Haq.
and we are
Team
Team Rusty
Rusty.
Car.
And this is our car. I'm going to talk a bit about the mechanical subsystem as well as the power subsystem. So for kind of all of the design and whatnot, here's kind of what the four sides look like, as well as we have this top part that you can fit upwards, and then here's kind of an inside look of the layout and whatnot. So for the mechanical design, I did pretty much everything in Onshape, and all of it was designed to be laser cut out of 1/8 inch cardboard and acrylic, as well as all of these stickers were also made at the Hive as well. In terms of the power subsystem, on this car we have a 5-volt buck converter as well as a 3-volt buck converter. And for the battery that we decided to use, we realized pretty early on that this needs a good bit of current and whatnot. So we have a 2S LiPo battery, so when it's fully charged it's about 7.4 volts, and it has up to 2 amps of current as well, so that ended up being plenty.
So I worked on the sensing subsystem of the car, which as you can see is the part that is on the bottom. This is what allows the car to sense the black line on the white background. So the way we designed it was through some IR photo sensors. As you can see, there are 4 sensors on the bottom, or these are actually the LEDs that shine the light onto the surface, and then it reflects back, and a lot of light will reflect if it sees a white surface and not a lot if it's black, and that will be picked up by these IR photodiodes. And depending on the more or less light that comes back to the sensors, there will be more of a voltage signal sent to the control system that determines whether the car is seeing black or white, and then determines whether or not it should turn.
So now I'm going to speak on the motion subsystem. So for motion subsystem, I used 2 motors, as you can see in the back of our car. It works concurrently with the sensing subsystems like just Cooper explained. How it works is sensing subsystems send control signals to a microcontroller, which we use ESP3266, and from that the controls goes to the DRV motor driver that we used to control the motors. Based upon the PWM signals that is sent, it decides how much turn to take. That's what motion subsystem is used for. As you can see on the screen right here, you can see this is what is our initial prototype for our cars. We initially put motors on a laser cut board, and we test run that to see how much weight it can take, basically for when we assemble our whole car.
Hello, I'm Ridwan, and I worked on the control integration and the audiovisual subsystem for our buzz car. And early on, each subsystem had its own sketch for sensing motion audio, but this made the robot hard to debug and keep in sync. So my job was to pull those pieces of code together into a centralized control program so that everything shares the same state and timing instead of behaving like separate projects. Firstly, I focused on feedback systems so that state changes would be obvious to anyone using the robot. The audio subsystem plays distinct 3-tone patterns when the car starts and stops, and I had to tune those so that they're clear and non-blocking. And the start sound finishes before the motion is enabled so that the car doesn't jerk unexpectedly. In parallel, the visual subsystem shows direction on the OLED and speed on the LED, and giving students a live view of how the controller is steering and how fast the car is actually driving. Once the feedback was working, I had to iterate on the wireless control. The first version was just a basic start and stop button, but this doesn't actually explain how the car was actually behaving and why it's drifting and hesitating on the track. So I turned that line car dashboard into a robot that now owns its own Wi-Fi network and serves a live car themed UI that not only starts and stops line following, but also streams telemetry data like average speed, direction, and the 4 IR sensor readings in real time. And this meant solving issues like sign conventions for left and right, making sure telemetry updates didn't interfere with the control loop, and altogether the iterative work across the whole team is not just resulting in a functional line follower, but the system's now integrated, observable, and most importantly useful in the classroom. Thank you.